Hi ladies and gentlemen, welcome to lesson 14. So today is a big lesson. We're going to take a look at how we're going to use RREF to set up the complete solution following along with what Strang has in his text for the problem AX equals B. We're going to look at different sizes of systems of equations, sometimes more equations than unknowns, sometimes more unknowns than equations. And we'll take a look at what the RREF gives us and why we really want to use this tool as opposed to anything else that MATLAB has to offer. So first things first, we're starting here in the linear systems excerpt that I've given you and a little bit of review here of section 2.4. Remember, 2.4 is about reduction to row echelon form. So the emphasis here is row echelon form, but not yet reduced row echelon form. And I just want to highlight the differences here and make sure that everybody understands. We talked previously about the fact that the pivots in row echelon form have been changed into leading ones. So we've scaled the equations so that we have leading ones in these positions. And you can look through here at the examples of things that are in row echelon form. All of these are. What I want to do is just highlight what is not row echelon form so that you understand. The definition is reasonably straightforward, although it's a little bit difficult to read through it. But what it's saying is that every pivot, every one of the, and now we're talking about a system that's has potentially free variables in it, that has linearly dependent columns, and so we don't necessarily have the pivots that are on the main diagonal anymore like we've been talking about previously. So the pivots have to be 1. So this one is not in row echelon form because it doesn't satisfy the requirement of having that pivot as a 1. The one above that doesn't satisfy because the pivots, which are here, here, and here, don't appear in echelon form. So echelon form is meaning that we're generally going to be working from the top left down towards the bottom right. It doesn't mean they have to be in a diagonal, but they do have to generally flow in this direction, and that's not what's happening here. And then finally, this is not satisfying the definition for row echelon form because we have to do a row swap to put the zeros down at the bottom. And we've seen this with what Strang has been talking about, where he has the RREF matrix and he eliminates the 0 rows. Those 0 rows are always on the bottom, so we need to be able to make that adjustment. A little bit of a go back here. We talked about elementary matrices just a little bit. Strang has talked about it a lot. This is my take on the elementary matrices. It's basically exactly the same as what we've seen. There is a little bit more information, for example, with these R matrices. Those are my elimination matrices. With these R matrices where we're going to go through and create leading ones out of our pivots. I also have the conversation of permutation matrices in here. So again, just a quick go back. Remember that Strang uses E for elimination, and that's his compilation of all the elimination matrices, and I have this R with the scoop over the top. This is the product of all of those elimination matrices together. But the idea is it's all exactly the same thing. So where we want to go now is to reduced row echelon form. And we can see from the definition here that reduced row echelon form is something that's in row echelon form, and then what we've done really is the Jordan part of the Gauss-Jordan elimination. We've used the leading ones to eliminate both below and above the pivot. And that's all this line says. It just says that we have to eliminate above as well as below. And so here are examples. And we can see that every column that has a leading 1 has nothing else in that column besides the leading 1. And that's the requirement. So here are some examples where we don't have that satisfied. So for example, here's a leading 1, but there's still a 1 in the column above that. Similarly, here we have a leading 1, but we haven't eliminated back up yet. So we have to eliminate in both directions. Let's talk about how this applies to our system of equations, right? That's really where we want to go. We're talking today in general. A is m by n. We could have more rows than columns, more columns than rows. We'll talk about that. What we want to do is look at the information that's being provided for us from RREF. And let me just orient you to what's going on. So we have B is the RREF for an augmented matrix. So just to be clear, B is equal to RREF of A augmented with B. And so what we're talking about here then is the letter K is being used to say that's the number of non-zero rows in B. Let's back up for a second and think about what we're doing. It's important to get the context of solving systems of equations. The systems are really constraints. They're constraints on the possibilities for the values in the x vector. And what it means to have 0 rows is that we have redundant constraints. So we could start out with a system that has 5 constraints, 5 equations, and when we hit it with the RREF, actually 2 of those rows become all 0, which just means that 2 of the constraints were linear combinations of the other 3 constraints. That's what the RREF is telling us. So it gives us, from the original set of constraints, it gives us an equivalent set of constraints where all the redundancy has been removed. That's an important aspect of what the RREF provides for us. That's why we have this conversation about K being the number of non-zero rows. K is the number of actual constraints on our system. Then it says that B is inconsistent if and only if we have in our last row, last non-zero row, the pivot is all the way to the right. So we already know this. What all this is saying, and that's why I want to highlight it, is it's not saying anything special. It's just saying whatever's happened up here, and we, of course, are going to start with a leading 1 and a bunch of zeros. But whatever's happened up here, the only way that I have an inconsistent system is if the pivot in the last column is down here in the last row. Right? If my last pivot is somewhere inside of that, then I have a consistent system. That's all it's saying. And then the last part here tells us something we already know, which is the number of free variables is equal to the number of non-zero rows, and we're going to subtract that from the number of columns. So let's be clear about what we have. What are the number of columns? So this is the number of columns in A, and that's where we have to be clear. So the number of columns, we're talking about n columns in the matrix A. So the number of columns is the number of unknowns. That's the number of elements in our x vector that we're trying to solve for. So it's the number of unknowns in our system. And then let's think about what k is in this case up here, right? What is k really? It's the number of non-zero rows. It's the number of pivots. So this is the number of pivots or leading ones in our system. What is that telling us about the system? It's giving us the rank of A. It's giving us the rank of our system. So this is really K equals the rank of the matrix A when we're talking about AX equals B. So all this really means, that second sentence is just saying if we take all the unknowns that we have and take away the number associated with the rank, which are the number of fixed variables, then what we're going to be left with are the number of free variables. Following are some examples that you're familiar with. This one's consistent, this one is a unique solution, and this one here has a free variable. And we'll talk about how we want to write down these solutions in a little while. But you definitely want to work through these examples, make sure you understand the definitions for fixed and free variables. A really important corollary here, which we've already covered, but let's just repeat it quickly. It says that if we have A, and we're solving now the homogeneous problem, let's be clear, AX equals 0, and we have A where A, of course, is m by n, but m is less than n. So we have more columns than rows. So we have an A matrix that looks like this. What do we know? Well, we know that the null space is non-trivial. We know that the null space of A is not just the zero vector. It has a greater dimension than that. There's more in the null space. And that's exactly the same as saying that AX equals 0 has an infinite number of solutions. So we know that x equals 0 is not the only solution. We know that this kind of squat wide matrix has more than one solution to the homogeneous equation. And there's a little bit of a demonstration in here. You can take a look at that. What I want to do now is really one of the emphasis points for what we're talking about today. We are going to look at how to write down the solution for a system of equations. So this matrix D is the RREF of A where we're solving the homogeneous equation. So let's be clear. We're solving AX equals 0. And then, so the augmented matrix is just A augmented with 0, but remember we never do that. We never include the 0 vector because of course the row operations are not going to change the 0 vector, so we just don't include it. So this is telling us that D is equal to RREF of A, which of course is the same as RREF of A augmented with 0, except we've removed the 0 column that would be here. And what we want to do is we want to say, how do we take this and turn it into the vector solution? Our goal is to write the solution as a vector, not just as, hey, x1 is this and x2 is that. That's not what we want. We want the complete solution as a vector. So the first thing we do from the RREF, of course, the row operations has not changed the solution to our system. And you remember that from our previous conversation is solving AX equals 0 is the same as solving the DX equals 0 with the reduced row echelon form. Keep in mind that Strang would be calling this here, right, in Strang, this would be the R. He likes to use the R for the RREF matrix. That's perfectly fine. I just want to make sure that you're following along with the differences here versus Strang. So we have the equations, and what we're going to do is we are going to write down a solution for each of the variables. So the first equation is going to give us x1. Looking up here, before we go through this, we want to look back up here and see how many unknowns we have. So the number of unknowns, which is the size of the x vector, is the number of columns in our RREF matrix, again, because this one has not been augmented. So in this case, the number of unknowns is 7. So we have x1 through x7. Then the other thing that we want to know is, what are the free variables? So the free variables are the variables, the columns associated with non-pivot columns. So this is a non-pivot column, this is a non-pivot column, this is a non-pivot column, and this is a non-pivot column. So we have 3 pivot columns, and we have these 4 non-pivot columns. So our free variables are x2, x4, x5, and x7. We have 4 free variables. So what we're going to do is we're going to take the equations that we have here, which have come straight from the RREF, and we're going to use them to write down what each of the entries are. We're also going to include, it seems pedantic and pointless, but trust me, it helps us to communicate better and avoid making mistakes. What we're going to do is, for each free variable, we are just going to write that free variable equal to itself. So the point is, the free variables are not showing up in here as something that we can set equal to other items because they're free. So we don't have an equation x2 equals with a bunch of stuff following it. x2 is a free variable. So we use the first equation to write down x1 equals. Then we have the free variable x2, We use the next equation to write down x3 equals, and then we have free variables x4 and x5. Then we use this equation to write down the solution for x6, and then we have free variable x7. The reason we want to write it in this manner is because we now have the x vector that we're after. So, very important point. The reason we write it this way is because we now have this x vector. We can read right off what the items in the x vector are going to be. So we write it this way so that we can represent this in vector form. Once we have the vector form, which is nothing more, you can see the collection, right? So let me highlight this in yellow. These are just the right-hand sides to all of the equations. These are just these right-hand sides here. All of these right-hand sides. And then finally what we do is we take that one single vector and we break it out because each of our free variables is going to have its own vector. So what we're going to do is we're going to take and remove, let me get the highlighter, we're going to pull out each of our free variables. And in this case, because it's ax equals 0 and not ax equals b, we don't have a particular solution. We only have the solution to the null space. And you can see, just to tie all this back together, each of these vectors here is one of what Strang calls special solutions. What we've done is we have taken the vectors and we have allowed each of the free variables to be equal to 1 and then set all the others equal to 0. So in this first vector, x2 is 1, and then x4, x5, and x7 are all 0. In the next vector, x2 is 0, and then we have a 1 here for x4, and a 0 for x5, and a 0 for x7, etc. So we're using exactly the same procedure that Strang's talked with us about for finding the special solutions, because really what we have is we have the solution to the null space. And if you think about, that's what this problem gives us. When we solve the homogeneous system, we are solving for the null space of A. That's what we're actually doing. So make sure that as we go through these, you practice this technique. You have to make sure that you have this down. Another important corollary here. So this corollary, again, is something that we know, but it's important enough for us to repeat it. It says, if we have A as a square matrix, so if A is a square matrix, then if we get an identity for the RREF, we know that we have a unique solution. So when A is square, if we RREF A and we get the identity matrix, we know we have a unique solution. Now, in reality, we wouldn't RREF just A by itself. We would RREF the augmented matrix. But if this comes out to be the identity along with what Strang calls the D vector, then we know that we have this unique solution. So that's all this corollary is saying up here. Okay, right here is one of the most important theorems in linear algebra. The reason it's important is because it tells us that RREF applies uniquely to every single matrix that we can come up with. And that's right, given a matrix B, there's precisely one RREF. So we can always find it, and it gives us a lot of information. And we will use the RREF to talk about the information that's coming from the matrix, about the matrix. We'll do that a little bit later. Right now, we're just focused on solving systems. But the president wants to tell us, that's right, this is a huge result. This is big because it applies to every single matrix. Those results are always enormous for us. This is not the only result that is that way, but it's one of the more important ones. All right, so down here, we have a conversation with an example. And what I want to do, I'm going to leave you to read this page 16 here. And what we're going to do is we're going to focus on what happens when we modify this B matrix here so that we end up with this RREF. Let me jump over to MATLAB and show you how this is going to work out. All right, so here's the B matrix. I've put that in there. It, of course, goes for quite a ways. Remember, you can always do carriage returns on that if you want. Then I've also extracted the coefficient matrix and the right-hand side vector because I'm going to show you a demonstration. So what we're doing is we are going to take and set up, for example, D, the D matrix, is equal to RREF of B. And let me just rerun this, and then here it is. And this matches exactly what we have over here. So there's really nothing to it. We just need to interpret and write down the result of what this means. We'll get to that in a minute. What I want to show you is the way that MATLAB is set up to solve is with the backslash command. And if I do A\B in this situation to try to solve, I get the following result. It tells me it can't solve. Well, this is one of the big restrictions of using MATLAB to try to directly solve systems of equations. We want to use the RREF because the RREF gives us the information about all of the solutions, which as ORs and data science majors is an important aspect of what we do for a living. We solve systems of equations. So let me write down then how we are going to do the solution for this item. First, I'm going to write down the equations. The first equation is, well, before I even get to that, I should figure out what's happening. I have this portion here is the RREF associated with the A matrix, and then I have the right-hand side over here, okay? And what we can tell is, we can tell immediately that this is inconsistent. We don't have a solution to this system. So what we'll do instead is we will take a look at what the RREF is telling us about A. So remember that when we RREF an augmented matrix, RREF A augmented with B, that's giving us two pieces of information. It's giving us the RREF for A, which Strang would call R, and then it's giving us the RREF for the vector as well, which is really giving us information about the solution. So we can use this front part of the RREF of the augmented matrix to have the conversations about what's happening with A. And what we can see here is what we've talked about previously. The first four columns of A, which, sorry, this is, yeah, so this was AX equals B. So we're solving AX equals B. I was just confused because I call this the B matrix, but that's the augmented matrix. So it's coming from AX equals B. So we know that the first four columns form a linearly independent set. Remember, the pivot columns, which are the first four columns, are associated with a set of linearly independent vectors that can be used when we write down the, from Strang, A equals C times R decomposition. So the C, in this case, would be the first four columns. And then the information provided in this last column tells us that the fifth column of A is constructed using this set of combinations for the first four columns. So we can build these things out. All right, so this is really it for using RREF. It is the way in which we are going to solve problems. It's the way in which we are going to write down solutions for not only homogeneous problems, but non-homogeneous problems as well. And let me just come back and emphasize this is the key dynamic here. And actually what I think I'm going to do, we have just a little bit of time, I'm going to provide you with an example of how we do this. All right, I've jumped back over here to the homework problems. And what we're going to do is we're going to take a look at problem number 6 here. Just so you know, and we'll talk about the participation questions in a minute, but your participation questions will be 2, 3, and 7. So you'll have those prepared from watching the video. But what I want to do is take a look at problem number 6. So I've put this into MATLAB, and I've entered in the B matrix here and then taken the RREF of it. And what I have is here's the B and here is the RREF. You see I have fractions over here. Those fractions are because I changed the format to rational. That's always a nice thing to use if you know that you're going to end up with some fractions to make things a little bit easier if you're not interested in trying to write down all the decimals. So since this is just an academic problem, that's what we're going to do is we'll take a look at these fractions over here. So I've copied the RREF for this system here, and let me write that or paste it in here. So I'm just going to paste that in here, and I'll expand this out for us. All right, so here's our RREF, and let's look at what this is actually giving us for the solution. We know a couple of things. We know that this is the RREF for A. So we know that we have fixed variables, x1, x3, and x4. These are the fixed variables, x1, x3, and x4. And for each fixed variable, we're going to be able to write down an equation. Then we have a free variable, and that's the x2 variable here. And remember, we determine that based upon pivot columns and not pivot columns. And then finally, we have the constants. This is the modification to our right-hand side vector from the Gauss-Jordan elimination. So let's write down our first equation. Our first equation says that x1 plus 2x2 is equal to 19/18. Right? And then our next equation says that x3 is equal to -2/9. And the last equation says x4 is equal to -1/9. Now remember, what we want to do is we want to write down the vector x. That's our goal. Our goal is to write down the x vector. Well, the x vector is equal to x1, x2, x3, x4. So we need a representation for each of those things. The x1 representation comes from our first equation. That's going to be equal to -2x2 plus 19/18. The x2 representation is, because it's a free variable, we're just going to write down x2. Again, it seems ridiculous, but we'll have to fill in every one of these entries. And once we do this, you'll see that what we're really doing with this approach is the same thing that Strang does to construct special solutions. x3 we see is -2/9, and then of course x4 is -1/9. And so this is our vector here. And what we want to do is take this and break it apart so that the free variable is multiplied by some vector. So we want x2, and now for each entry, what does x2 multiply? Well, it multiplies -2, it multiplies 1, and then the last two equations didn't have an x2 in them. So those are 0. So this is the vector that's being multiplied times our unknown. We also know from having talked about the null space that this vector spans the null space of A. So whatever the A matrix was that gave us the first 4 columns here in B, right, which is exactly these first 4 columns, we know that it has a null space vector that looks like this. That's part of the information that we get from the RREF. And we'll talk more about that later. But then what we have is we have the rest of the equation. So the rest of the equation are the constants. The constants are 19/18 and 0 and -2/9 and -1/9. And now this representation is the solution to the problem. We see that we have a free variable. We see the direction that that free variable is actually influencing the solution. And then we have what Strang calls a particular solution. So that is the correct terminology. This is the particular solution. There are an infinite number of particular solutions we can pick. This one was selected because we have set the free variable equal to 0. That's the most common way to do it. That's what Strang talks about in his text. So we could have any particular solution here, which would be this vector plus any amount of the free variable direction vector here, the special solution vector. But we just are going to pick the free variable equal to 0. All right, so let's talk just a quick minute about what this means. This is called an underdetermined system. So it's underdetermined because we have free variables. We have the ability to actually turn the x2 knob to come up with some desirable quantity, some desirable solution. This is the whole idea behind optimization. We have a set of constraints and we have an objective function. And we have to satisfy the constraints. Oftentimes those constraints are inequalities as opposed to just equalities. And you'll learn more about that if you take OR classes. But we have this set of constraints, and what we're interested in when we have an underdetermined system, we have free variables. And we want to optimize our objective function. So maybe that's the fastest time, maybe it's the lowest cost, maybe it's the greatest revenue, whatever it might happen to be, we have the ability to turn this knob, still solve the problem. In other words, still satisfy the constraints, but we can use this knob to make our objective function optimal. And that's how operations research is really set up and running. So that's it for the example. Let me just throw up the reminder for the participation problems. The participation problems are the ones that I've already discussed, 2, 3, and 7 from section 2.5. These are already homework problems, so you're just going to have these set before you show up to class. Make sure you've got the fundamentals of these ideas. Thanks very much, and we look forward to seeing you in class.